pleasure to introduce Donghoon Jang, who will be talking to us about this.
Okay, thank you very much. Today I'm going to talk about my work on subcollections on four-dimensional almost complex manifolds with isolated fixed points, which you may regard as an extension of the classification of four-dimensional Hamiltonian S1-spaces to almost complex manifolds. Four-dimensional Hamiltonian S1-spaces are classified by their graphs. We will discuss on the extension of this to almost complex manifolds, but only in the case of isolated fixed points. For a subcollection on a four-dimensional almost complex manifold with isolated fixed points, we will classify weights at the fixed points. We will show that there is a combinatorial object, a graph, which encodes the data on the fixed point set, and there are a minimal graph and operations that attain any such graph. As an application, we will be able to provide a necessary and sufficient condition for the Chern numbers of such an action. And actually, we achieve by demonstrating that pairs of integers that arise as weights of a circle action actually also arise as weights of a restriction of a T2 action. So an almost complex manifold is a pair MJ where M is a manifold and J is a map on its tangent bundle, which is a vector bundle isomorphism whose square is minus the identity called an almost complex manifold structure. Every symplectic manifold is almost complex. I'm thankful to speakers of this morning session for introducing many definitions that I need. So let the circle group act on an almost complex manifold M. And during this talk, we will assume that any group action on an almost complex manifold preserves the almost complex structure, or J holomorphic, that is J composed DG is equal to DG composed J for all elements in the group. And let P be an isolated fixed point, then the circle acts on its tangent space by using complex coordinates. It acts by multiplication by some power of G. Here N is 2n is the dimension of the manifold, and those exponents WPIs are non-zero integers, and these non-zero integers are called the weights at P. And let me define the index of P as the number of negative weights at P. As I said, we will classify weights at the fixed points in terms of a combinatorial object graph. So let me give you a definition of a multigraph. So a multigraph is a pair where V is a set of vertices and E is a set of edges. A multigraph is called directed if every edge has a direction, which means there are maps I and T giving the initial vertex and the terminal vertex of each edge. We say that a multigraph is labeled if every edge is labeled by a positive integer. So in other words, there is a map W from E to the set of positive integers. And for each edge E, we will say WE is the label of E. Now let gamma be a labeled directed multigraph, and let E be an edge. We will say that I of E, T of E is WE edge. Alternatively, we will also say that T of E, I of E is minus WE edge. And for a vertex V, we will call this multiset the weight set V. So what we do is the following. So we consider all edges of V. If the initial vertex of an edge is V, then we collect plus of the label of that edge. And if the terminal vertex of an edge E is V, in that case, we collect minus of the label of that edge. Now let S1 act on a compact almost complex manifold M with isolated fixed points. We say that labeled directed multigraph gamma describes M if the following conditions hold. First, the vertex set of the graph is equal to the fixed point set of the manifold. And second, the multiset of the weights at a fixed point P is equal to the multiset of the weights of a corresponding vertex. And for each edge E, its initial vertex and its terminal vertex, those two fixed points are in the same connected component of this isotropy submanifold M sub zima WE, which is the set of points in M that are fixed by this subgroup zima WE, where this subgroup zima WE is a cyclic subgroup of the circle group. Now let's specialize into the case of dimension 4. So let M have dimension 4 and let gamma be a multigraph describing M. And let E be an edge. By definition, W of E is a weight at the initial vertex, which is fixed point, and minus WE is a weight at the terminal vertex. And those two vertices, or those two fixed points, are in the same component of this isotropy submanifold. If the label of the edge is bigger than 1, then F is an isotropy 2 sphere. On the other hand, if the label is 1, then this subgroup is just a trivial group, so F is nothing but the manifold M. Unfortunately, a multigraph describing M need not be unique. So for instance, consider the diagonal action on CP1 times CP1. It has 4 fixed points, and all the weights are +1 or -1. And these are two different graphs, but they both describe this action. So I and Tolman showed that, so here M need not be 4-dimensional, just arbitrary dimensional. If there is a circle action on a compact, almost complex manifold with isolated fixed points, then there always is a label-directed multigraph describing the manifold with some technical condition that for each HE, the index of the initial vertex in the isotropy submanifold is 1 less than the index of the terminal vertex. In particular, the multigraph has no self-loops. And when M have dimension 4, this is Cartesian's graph for a Hamiltonian S1 action if we do the following. If we remove any edge with label 1, and if we assign the moment image to each fixed point. Now let me illustrate this definition with examples, specific examples. So let us consider a linear action on CP2 in that way, where A and B are positive integers. This action has 3 fixed points, and the weights at the fixed points are a plus b comma a minus a comma b and minus b comma minus a minus b. How do we show this? So for instance, the fixed point P2, 0, 1, 0, has local coordinates z0 over g1 and z2 over z1. And the circle group acts near this point using these local coordinates this way. G acts on z0 trivially from the given action, and G acts on z1 by multiplication by g to a, and G acts on z2 by multiplication by g to a plus b, and so on. And then you simplify, then you see that the weights are minus a and b. So on this manifold CP2, we have this action and 3 fixed points and those weights. And this figure, this graph, describes CP2 with this section, which means, so there is an edge from P1 to P2 with label A. So P1 has an outward edge with label A, which means P1 has weight plus A, and P2 has an inward edge with label A. So we give P2 a weight minus of that label. And same thing for other fixed points. One more example. So fix on integer n. The Hertzberg surface sigma n is defined as the set of points in CP2 times CP1 that satisfies that equation. Z1 W to the n is equal to Z2 times W1 to the n. And let C and D be positive integers such that C minus ND is not equal to 0, so that we get isolated fixed points. And let S1 act on this Hertzberg surface in that way. And you can do the same thing. This action has 4 fixed points, and you can, using local coordinates, you can compute weights at the fixed points. So we have the action, fixed points, and weights. And this is a graph describing the action depending on 2 cases where C minus ND is positive or negative. Let me tell you some history about circle actions on manifolds. So on complex side, Carrel, Howard, and Kosniowski proved that holomorphic vector fields on a compact complex surface with isolated zeros can be obtained from CP2 or a Hertzberg surface by blow-ups. On the symplectic side, the same is true. A Hamiltonian 4-dimensional Hamiltonian S1 space with isolated fixed points can also be obtained through blow-ups from CP2 or a Hertzberg surface. So this is by Carson after a preliminary work by Ahara, Hattori, and Adim. What I need to tell you is both cases also studied the case of non-isolated fixed points, but during today's talk, let me just focus on the case of isolated fixed points. In particular, these results classify weights at the fixed points. As I said, we will discuss an extension to an almost complex manifold by showing that for a circle action on a 4-dimensional compact almost complex manifold with isolated fixed points, a graph describing it can be obtained from a minimal graph followed by a combination of 4 types of operations on the graph. So what is a minimal graph? Let me say a Our multigraph is minimal if the following conditions hold. First, each edge has label 1. In other words, every fixed point has weight +1 or -1. And for each edge E, the index of the terminal vertex of an edge is 1 more than the index of the initial vertex of the edge, where for a vertex V, NV is the number of edges whose terminal vertex is V, so that it agrees with the index of a corresponding fixed point. In my paper, I called this graph in a different way, but let me say this is a minimal graph during this talk. From definition, a two-valent minimal graph has 4k vertices. The number of vertices is divisible by 4. So now, what are those 4 operations? This is operation 1. Suppose you have A edge and then B edge. And then what operation 1 does is to replace the middle vertex by an edge whose label is the sum of the labels of 2 edges. Now this is operation 2. Suppose you have C edge, D edge, and then C edge. Then what operation 2 does is to replace the label of this middle edge by the sum of the labels of these 2. Yeah.
Is there some geometrical construction?
Yes. Yes.
Is
Yeah.
it easy to hint what
Yeah.
it might be?
Yeah. This is so. At the time that I wrote this paper, I didn't realize this, but later I realized that this can be realized as a combination of a blow up and blow down.
Oh.
So what you do is, so DCT, you blow up this fixed point. And then you blow down, yeah, this should go. Yeah, and then you blow down this edge, this 2 sphere. Yeah. Thank you for your question. Operation 3 is just vertical symmetry of operation 2. So suppose you have E edge, F edge, and then E edge this way, then what operation 3 does is to replace the label of the middle edge by the sum of the labels of these 2. And operation 4 is more complicated, but this it can be also realized as a combination of blow up and blow down. So suppose you have G edge, H edge, G edge, and then H edge. Then what you do is you remove these 2 edges. You remove this vertex, and then just draw one edge whose label is the sum of these 2 labels.
So can you do that instead of having 4 operations, just as well to blow down?
Yeah. So, so that is going to be like a geometric classification. This is going to be like a topological classification, I can say. And this classification has an advantage of somehow relating to like some extension to T2 action, etc. I'm going to explain it. So this is the main result. So there is a subcollection on a four-dimensional compact almost complex manifold with isolated fixed points if and only if a graph describing it can be obtained from a minimal graph followed by a combination of the four operations.
Maybe I will elaborate this just a bit. Are you allowing the operation in the opposite direction as well, or just one direction?
Just one direction in this paper. So as an application, moreover, if the manifold is complex or symplectic, then a graph describing it can be obtained just from this graph, followed by the four operations.
What about CP2?
CP2, so we begin with this, and then if you use operation 2 or 3, then you can replace this labels, and then you use operation 4 to remove this, and then C plus D. Yeah. Yeah, thank you for asking. A key ingredient to prove this theorem is equivariant plumbing. So let me explain plumbing and equivariant plumbing. So suppose let E1 over M1 and E2 over M2 be two rank n vector bundles over two n-dimensional manifolds. And let Pi be a point in the base, Mi, and let Di be a ball about Pi, and let Di prime be a ball about Vi, which is in the fiber over Pi. And F1 is a diffeomorphism from neighborhoods of a point in base to neighborhood of a point in fiber of the second manifold, and F2 is the opposite way. The plumbing of E1 and E2 at P1, V1 and P2, V2 is the quotient where F is defined by F of X, Y is F2Y, F1X. So in other words, you glue base of the first manifold with first vector bundle with the fiber of the second vector bundle, and you glue fiber of the first vector bundle with the base of the second vector bundle. Now let's focus on n equal to 2 case, and let a torus S1 or T2 acts on E1 and both of E1 and E2. Suppose that P1, 0 in E1 is a fixed point of this torus action with weights W1 and W2. Let me say W2 is the weight of the fiber. And suppose P2, 0 in E2 is a fixed point with weights W2 and W1, where W1 is the weight of the fiber. And then in this case, we can plumb two bundles at these 2 points equivariantly. Now, this is important for construction, which is a reformulation of Mazda's work in 1909. Suppose we actually have k vectors, but for some technical reason, I also put v naught and vk plus 1. So let v1 through vk be a sequence of vectors in Z2 in counterclockwise order. And suppose that each successive pair is a basis of Z2. And for each I, there is an integer ai such that the next vector, vi plus 1, is equal to minus ai times the middle vector minus the previous vector. then what we can do is we can construct a four-dimensional closed almost complex manifold equipped with a T2 action having k fixed points P1 through Pk such that the T2 weights at the ith fixed point Pi are ith vector Vi and minus of the previous vector minus Vi minus 1.
Just to clarify, are you aligned to go around more than once?
Yes, yes.
So this is a multi-fan.
Yeah.
You still with a compact, almost compact.
Yes, yes.
Did Masuda give an almost complex structure?
Yes. In addition, suppose that for each I, its first component is not 0. Then we can say more. If we consider the first S1 vector of the two-dimensional torus, then the S1 action on M has the same fixed point set as the T2 action. And the S1 weights are just first components of the T2 weights. And let gamma be a labeled directed multigraph such that Pi, Pi plus 1 is Vi, 1 for each I. Then gamma describes M for the action of the first S1 vector. Let me give you an example to understand this. So for instance, if we take V1, V2, V3 as 2, 1, 3, 2, and minus 5, minus 3, then those three vectors satisfy the conditions in the previous slide. And the graph we get, you just read the first component, so it's 2. So first label is 2, the second label is 3, and then the third label is minus 5, which goes from P3 to P1, but we will reverse the direction and then also reverse the label. If you use this construction of Masuda, the manifold you construct is CP2. Okay. For this construction, I need to explain holomorphic line bundle over CP1. So let A be an integer and let OA be the holomorphic line bundle over CP1 whose self-intersection number of the zero section is A, which is the quotient of C2 minus 0 times C by the C star action given this way. And let bracket Z1, Z2, W be the equivalent class of this point. And let T2 act on this bundle this way. So it acts on Z2 by multiplication by T2 U1 and then W by T2 U2. First, where U1 and U2 are some elements in Z2 that form a basis of basis. And let dA U1, U2 be the disk bundle of this line bundle with this action. So this action has two fixed points, 1, 0, 0, Q1, and Q2, which is 0, 1, 0. And again, using local coordinates, you can compute the T2 weights at these fixed points. At Q1 is easy. Yeah. You just use Z2 over Z1 and W over Z1, then weights are just U1 and U2. And at Q2, because of this relation, you will need to subtract, multiply by A to U1. So we described this bundle with T2 action and fixed points and weights. Now we go back to this theorem, the situation of this theorem. We assumed that for each I, Vi and Vi plus 1 is a basis of Z2, and then especially part B, that for each I there is an integer Ai such that Vi plus 1 is equal to minus Ai Vi minus Vi minus 1. So for dAi Vi comma minus Vi minus 1, the T2 weights at Qi2 are, as I explained, this. Instead of for U1 you put Vi, and for U2 you put minus I minus 1. And similarly for the next one, we know the T2 weights now at the first fixed point are just these two. So it's Vi plus 1 comma minus Vi. But by assumption, these two are the same. Vi plus 1 is equal to minus Ai Vi minus Vi minus 1. But their orders are different. So if we want to glue together, we need to plumb equivariantly. So for each I, we can equivariantly plumb these two bundles at those two fixed points. And you do this for each I. For each I, you plumb equivariantly. At the next step, you plumb equivariantly. Then, if you do this, then you don't get a closed manifold, but you can make it closed. Its boundary is S1, just S1 times D2, so you can make it closed.
But then you need to extend the almost complex structure.
Yes, yes, yes. So as Yael asked, if the winding number of the vectors is 1, then this manifold is projective, so Kähler. But if the winding number is bigger than 1, then no. So the number of times Vi wrap around the origin.
So you need to make sure there's no obstruction to extending the almost complex structure.
Yeah, right.
So what's the relevant?
But you say there never is.
Something needs to be simply connected, right?
Mm-hmm.
GL 4 plus 4 mod.
Mm-hmm.
Some quotient. Okay, never mind. There's something needs to be simply connected to be able to extend it.
Mm-hmm.
SO4 modular U2.
Yeah, something like that. Yeah.
But you're saying that this is all in C.
Yeah. Yeah, thank you. I need one more technical definition. So suppose we have connected two regular labeled directed graph. We say that the graph extends to Z2 if we can label successive vertices by P1 through Pk, and we can choose a sequence of vectors. So it's much like the conditions in the theorem in counterclockwise with so that this condition holds, which is exactly like the conditions in the theorem. That each successive pair is a basis of Z2, and this equation is exactly the same, and the last condition is also same as in the theorem. And you can think of this definition as a graph for an S1 action can be extended to a T2 action. So this is a proposition. So suppose two regular labeled directed graph extends to Z2, then you can construct a four-dimensional closed almost complex manifold with T2 action having isolated fixed points such that that graph describes M for the action of the first S1 vector of T2. And the idea is just to use the equivariant plumbing construction in the previous theorem. So this was the main result, that there is a manifold if and only if a graph can be obtained from a minimal one by four operations. And we proved this theorem by showing that that graph is obtained from a minimal graph by four operations. And we show any minimal graph extends to Z2. And suppose you have a graph gamma, and you apply one of the four operations, and you get gamma prime. And then if gamma extends to Z2, then gamma prime also extends to Z2. If we prove these three steps, then it will prove this theorem. So let me do some of the proof. The first step is, of course, we need to show any minimal graph extends to Z2. And what you need to do, according to the previous theorem, this theorem, what you need to do is just to find appropriate VIs. For instance, you can take those VIs, like 1, 0, 1, 1, and then minus 1, 0, and then minus 1, minus 1. And you repeat them. Then, first of all, you will have one edge because we take 1, 0. And then the next vector is 1, 1. So you just look at the first component. So that's going to be the label of the next edge. And then the label of the next edge is going to be the first component of the next vector, which is minus 1, which goes this way. So you flip the direction and then take the minus of the edge. And then you keep going on.
So there will be 8 and 980 also.
Yes, yes. Yeah.
There's no issue of making sure things are consistent if you prove.
Yeah, yeah, yeah.
It's okay?
Yes, okay, yeah. And then this is about operation 2. Suppose we have so our graph gamma has this kind of part, and then you apply operation 2 to get a new graph. And then if the original graph extends to Z2, then the new graph also extends to Z2, and the proof is you just need to find right new vectors that satisfy those conditions. Because we assumed the original graph extends to Z2, we can label vertices of gamma by P1 through Pk, and there is a sequence of vectors V1 through Vk in counterclockwise order that satisfy these conditions. And then let's define new vectors in this way, where we take the sum of, so VIs, so we had V1, V2, V3, etc. But now V1 prime is same as V1, but for V2 prime, instead of V2, we add V1 here. then this new graph extends to Z2 with these new vectors.
Can you say something about why does the extension match up and go through loop of edges?
Yeah, that.
Like what ingredient goes in there? Some ingredient that is relevant for showing that.
So, we need to show that these new vectors also satisfy the conditions of the theorem. Like for instance, there are new AI primes that satisfies these equations. But as long as your vectors satisfy this all of this, then no problem.
Can you go back to the, hold on. Okay, yeah.
This one?
No. One more?
One more?
One more?
One more? Okay.
One more? One more? Just one more? No, are you going backwards or forwards?
I'm going backwards.
No, I want forwards.
Forwards, okay, sorry.
The extension, how do you extend? So if you extend one, then you know how to extend the next one, right?
Yeah.
Did you have a slide on that? Okay, hold on. Did you? Okay, maybe I'll. Okay.
So what we have discussed so far obtain a kind of extension result. Suppose you have a collection on the four-dimensional compact or most complex manifold M with isolated fixed points. Then what we have shown is we can construct another manifold which is equipped with a T2 action, such that if you look at the action of the first S1 vector on this new manifold M prime, that one has the same graph as the graph for M, which means M and M prime have the same weights. And the proof is, a graph describing M is obtained from a minimal graph and by 4 operations. And so this graph extends to Z2. So by using the construction, we can construct such a manifold M prime. Silvia Sabatini asked what possible term numbers are for a subcollection on an arbitrary dimensional manifold with isolated fixed points. And in particular, in dimension 4, Silvia asked if the Miyaoka-Yau inequality C1 square less than equal to 3 times C2 holds for such a manifold, which is true for a Hamiltonian action. In dimension 4, C1 square is 10 times N0 minus N1, where Ni is the number of fixed points with index I or with I negative weights. And C2 is the total number of fixed points, which is 2 times N0 plus N1. I mean, because it's the total number of fixed points is N0 plus N1 plus N2, but N0 and N2 are equal, so we get this. Because of these two, that inequality is actually equivalent to saying if N1 less than or equal to N1 holds. In the case of a Hamiltonian action, there is a unique minimum for the action. So there is a unique fixed point of index 0, which means N0 is 1 and N1 is always positive. So this inequality holds. But for almost complex case, N0 and N1 are at least 1, but they can be arbitrary. So let N0, N1, and N2 be integers. There is a subcollection on a 4-dimensional manifold with N0 fixed point of index 0, N1 fixed points of index 1, and N2 fixed points of index 2, if and only if N0 and N2 are equal, but otherwise N0, N1, and N2 can be positive. And in this case, the top genus of the manifold is N0. In particular, C1 square less than or equal to 3, C2 need not hold for almost complex case. So there is a manifold, 4-dimensional manifold with these two term numbers if and only if N1 and N2 are positive integers. So as a corollary of the main result, we determine the term numbers of such a manifold. And this is the end of my talk. Thank you.